Hello, everybody, and welcome to class. Today, we are going to expand our skill set of find overlaps. We've worked on finding overlaps between our chip peak files and understanding genomic ranges of annotation features, and now we're going to find the overlaps between the two of them. Where do our peaks land in the genome relative to known annotations? And so let's get started. And we're at class 2023-04R Basics, number 6, overlapping analyses of our data. Okay, and I'm going to use the same code here in my R Studio. So what our goal today is to take our peak files and overlap them with promoters, gene bodies, link RNAs, mRNAs, and compare them. So we've been sticking with this POLR2A data set of 4 replicates and 2 inputs. We've run that in the O3 Nextflow classes, and we're just going to stick with that for now. And then after this section, we're going to move to your custom data set and start running these again. So we're going to keep seeing these patterns over and over again as we expand to your custom data set. Okay, so I'm just doing the space path so we don't overwrite stuff and get mixed up. You would have that. And then the path to your peak files is here. If you've cloned class the same way, this will be the same thing. And we're using rtrack layer import to import these peak files as genomic ranges. And we're doing file path, pasting together the text of where it is, just so we don't get lost. So you want to set this up right. And I've already done that. I've also uploaded, we're loading our GenCode GTF that has all the genome annotations as genomic ranges, and we use rtrack layer import. The previous videos show where you can get this data set and download it to your own computer, and then just put the file path in there. Okay, so let's start importing peaks. Okay, got 1, 2. And then I've already loaded GenCode GR. This takes about 5 minutes, so I did that ahead of time to get going. So we're going to see the same indexing we did almost the entire last class, where again we're going to take a GenCode GR object here that has all of this data that we went over in the last class, like gene ID, gene type, transcript name, exon number, et cetera, in this genomic ranges object. We're going to index in there with the square brackets to subset out the data that is just genes. And we're going to define the promoters, not the TSS like we did last time, but now we're going to say upstream in this promoters function is 1 kb upstream and 1 kb downstream. So the parameters for promoters are the data frame, which we've indexed into just the gene objects, and telling it how much upstream and downstream you want. Okay, so let's run that and get our promoter regions. So now we have a list of promoters, where's GenCode promoters here, and it's 60,609 long. That's the same as the length of genes in GenCode here. Sorry, that's the wrong entry. So that basically that says we have 60,000 promoters, 1 for each type of gene. And so we can length that as well instead of looking in the environment, and we see the same number. Okay, so let's find how many of our peaks in peak file 1 overlap with this new promoters we've just made. So we just made GenCode promoters, which is the 1 kb upstream and downstream I range or window of a promoter. And now we're going to find overlaps with our peak file, just simply using find overlaps. From the previous class, the key thing to remember is find overlaps will give us @to and @from, so we can know where the overlaps occurred. We also went over some other ways of doing it, and we'll continue to use multiple ways to find overlaps and think about them. Okay, so we're going to run that. Our peaks, so find overlaps arguments are the G range 1 and G range 2, and this will be @from and @to. Okay, so run that. And we see the warning about the weird chromosomes. That's fine. We'll deal with that in a bit. And we can see the length of this is 60,609. And we see that 19,000 objects overlapped already. So that's pretty good. And then we can see the same for our peak file 2, do the same thing, overlaps with the GenCode promoters object we just made. And here we see that there are 19,700. So about the same number of promoter overlaps. And remember, we have 60,000 total. So we can already start to understand that about a third of the promoters are bound by polymerase 2. Okay, so now what we want to do is take this a little step further. And let's say you did replicate chip experiments, which we've done here. We have 4 replicates. And we want to say a conservative approach is saying, let's find the replicates that are in all the peak files. So in this case, let's say we only have 2 replicates, peaks 1 and peaks 2. And we can say, what are the promoter overlaps between, or the peak overlaps between peaks 1 and peaks 2. So now we're going to do this. This is a bad object name that I'm assigning this to, but I don't want to change it to refactor everything. Okay, that didn't work. So why not? Well, it turns out the findOverlaps is giving us in peaks in the promoter overlaps here. What we're seeing is that the @to and @from are not able to be intersected. And that's the advantage of findOverlaps, is that we have the @to and @from, so we can see the perspective of the subject into the query and vice versa. That's what the issue is there, is that this is a bunch of @tos and @froms and promoter overlaps and the indices of which ones overlap. We can't do it that way. So our goal is to overlap our peaks files, and we can't do the overlaps of the overlaps. So we took each peak file, found the overlaps with promoters, and then found the overlaps of those two is not possible, because that first overlap gave us the @to @from output that we can't then overlap again. So I just wanted to point that out, because that's a common thing, especially once you get over multiple files. And so the way we can do that is by making a new object, indexing in to the @from and @to, and finding out what the peaks are. So this is going to be peaks overlapping the promoters from peaks 1. So the peaks 1 file overlapped with the 60,000 promoters. We're square bracket indexing to subset out, and we're taking out the unique overlaps in @from. In the previous class, we went over this @from and @to and how multiple overlaps can occur. And so we're just taking the unique number of overlaps that there are in here. So this will give us an object that is just peaks that had overlaps and their coordinates. So let's take a look at that. So if we look now, we can see that we have this seq info with the chromosome and the element metadata and the list data of things like the name of the peak, the score, p-values, where the data sort of hides. Let's get back to it, and we can do the same thing for peaks 2, is just say, give me the unique peak values in the @from, so the ones that had one overlap with a promoter. Okay, so then we do that, and the same thing. And so now we have 2 G-range objects that we can find the overlap to. We're just going through this stepwise. We'll do this much more succinctly in a minute, but it's just good, more overlaps practice and @from and @to. Okay, so now we can find the overlap of the overlaps by taking the peaks that overlap promoters in peaks 1 and peaks 2. Now that we've converted them to that, and if we look now, what we can see is 14,403, 12,961 overlaps. And so that were in common, and each file had about 13,000 or 14,000. So that's about 90% of the overlap events at promoters occurred in both peak 1 file and peak 2. So that is the stepwise way of doing it. You need to have 2 GRange objects to do find overlaps, and the output is going to be at from and at 2. And so what we can do now is subset by overlaps, where we will still retain the information of where the overlaps are and not in an at to, at from way. So there's some advantages and disadvantages to all of these approaches, but we'll go through them now. Okay, so subset by overlaps is the same sort of inputs. What's your first GRange and your second GRange? Again, you want to sort of think about the order when you're doing this. And so I'm going to subset peaks 1 by GenCode there. And so if we take a look at this now, here we can see the length is 13,857, which is the same as it was above. Okay, so it finds the same overlaps basically. Subset by overlaps for peaks 2 is just comparing this to them. This is that warning of the contigs again. It's not a big deal, and we can take a look at that and see. Should have made this bigger. The same 14,403 as we did before with find overlaps. Okay, so that's good to know. Subset by overlaps gave us the same number of overlaps between a peak file and the promoter file. Okay, so now we are going to do the overlaps between the same way we did. So we've made an object using subset by overlaps of peak 1's overlap with promoters, peak 2's overlap with promoters, and now we're going to find the intersection of those. And so we'll do find overlaps with the promoter overlaps of the whole peak 2 and 1 that we just made up here. And then let's take a look at it. So let's see. Here we get that warning again, and now we're just going to take a peek. So we see it's 12,961 overlaps again between the two. So it's the same as up above, but a little easier to use, that we could just do it in sort of 1 step instead of 2. Okay, so let's see. We went into sort of at 2 and at from length before, and I think it's just important to sort of reiterate that here, so we can use base R code to look and find how many unique peaks resulted in the overlaps. So here what we're doing is we're using unique subset by overlap peaks. That's here, where we just made that subset overlap peaks, which is now the overlaps of the overlaps. So the 12,000 values. And so if we look at where those came from, which is the subset is from 2, is from the promoter's perspective, and we can see the length of unique values in that data frame. It's 12,482. So that means that we had some that had, most of them only had 1 overlap. Promoters, from the promoter's perspective, they only overlap with 1 peak. And so this is the same thing. And so these are basically, we can see how that happened, because that means that the subject file, the overlaps between peaks 1 and peaks 2 to promoters to each other, is here. So we can see that most of the peaks only had 1 overlap, some had 2, some had 3, and some had 4. And so this length unique gave us the total number of overlaps, and that had 1 sort of entry to them. Okay, so the numbers are here. I'm getting funny numbers right now, but this is how this all adds up when you run it. So there's 12,482 unique peaks that overlap 12,961 promoters. Okay, so that's really good. 90% of our peaks overlap. And so what we can do here is let's just start fresh, clear our memory. This is a lot of overlaps, but it's important. So let's go through it again and do it a little simpler. So we can do our peaks 1 and peaks 2 are our peak files. We'll do subset by overlap and call that the consensus peaks, or the peaks that are the same between the two. Okay, and that is our G-range objects of the overlaps of peaks 1 and peaks 2. So if we look at how long pole 2 peaks 1 is, what is it? Excuse me. So we see there's 33,582 objects in peaks 1. That's the number of peaks. And in peaks 2, we can see that, well, we can see it from here, 33,000 and 43,000, or we can just click on it and look at it. So now what we can do is take that consensus peaks. So now we've overlapped the peaks first, and then we'll overlap them with promoters. So we're going to use subset by overlaps. The first object that we're going to try and overlap with is our pole 2 consensus peaks we just made with GenCode promoter regions. So these are being peaks that are in both files that overlap promoters. Will be what this pole 2 consensus peak OB promoters object looks like. And now if we look at it in here, we see the, where is it? Well, it's getting busy on this terminal, so let's just see it this way. We can see it's 12,331 long. So that means that 12,000 of the starting peaks of 33,000 and 43,000 overlap promoters. So they might be overlapping other regions, but it does sort of important to sort of see that not a smaller fraction of your peaks, even though they're very consistent in overlapping promoters, which we did first, 90% of the same promoters overlapping the chip data. And here we can see now that it's only a small fraction of the total number of peaks that is the overlapping promoters. Okay, so now there's more information about the numbers and thinking about overlaps. And so we're going to do subset by overlaps between oh, sorry, go ahead and just do this on your own. It's just the same code we did before with at from and at to. I guess it is the last thing to do here. So what we're doing is we're comparing promoter overlaps with peak 1 files. So peaks that overlap promoters in file 1 and file 2. And we're doing the subset by overlaps. You can see it here. And we get 12,257 unique overlaps. And then we can now overlap these two and see if we get the same answer using subset by overlaps versus findOverlaps. And with both methods, what we see is 12,257. So that's good that we get the same result using both methods. And you can start to see now about why we've lost the at from values in using subset by overlaps. Okay, so that's a lot of overlapping, but what we can do now is see overlap peak files, and now we can overlap the overlaps with genome features and find out where they're binding. And that's what we're going to do moving forward. So we'll use these same approaches And this is really just to get you familiar with different forms of doing overlaps, specifically find overlaps versus subset by overlaps, going back and getting a feel for what those two differences are. And then I have an exercise here of taking your 4 replicate pull2 peak files and trying to find the peaks that are in all 4 and keeping their ranges. Here I have a solution I'll post later. And here's some questions for you to use the code up above, put it into a small chunk and run it. So you can sort of use those subsetting and overlaps on your own. Okay, with that, thank you very much and be well.